This presentation is an introduction to steam turbines. A steam turbine is a device that converts the thermal energy of steam into mechanical energy by using it to turn the blades of a rotor. Purpose: steam turbines are the prime movers driving the generators found at many different types of plants, including petrochemical, thermal, geothermal, and nuclear power plants. Steam turbines widely used as drivers for large ships, while smaller steam turbines are used to drive pumps and fans in petrochemical plants. Thus, while we may not see them every day, steam turbines are connected to our daily lives in many ways. Steam turbines, working principle. How do steam turbines work? First, we have to look at the basics. Energy can neither be created nor destroyed. Energy can only be transferred from one form to another. Natural gas burners transfer chemical energy to thermal energy, on an industrial scale through heat exchangers, to produce high temperature and pressure steam known as superheated steam. This is a photo of a steam boiler used to create superheated steam. Steam turbines use thermal energy from steam and transfer it into mechanical energy to turn a shaft. The turning shaft moves equipment like generators or pumps depending on the process need. When you press the end of a garden water hose, the water speed increases and falls on a longer distance. The pressure energy of the water is converted into kinetic energy, and so the speed increases. This kinetic energy can be transferred to machines. Superheated steam drives steam turbines. Steam contains thermal and pressure energy. When steam is released through a nozzle directing onto turbine blades, thermal and pressure energy is converted into kinetic energy. Pressure and temperature of steam both decreases after leaving the blades of the turbine. Kinetic energy, found in steam, is converted into mechanical energy by rotating the turbine. Note: kinetic energy is the energy an object has due to its motion. Convergent and divergent nozzles. A nozzle is a duct that increases the velocity of the flowing steam at the expense of pressure drop. A duct which decreases the velocity of the steam and causes a corresponding increase in pressure is a diffuser. The same duct may be either a nozzle or a diffuser depending upon the end conditions across it. If the cross-section of a duct decreases gradually from inlet to exit, the duct is said to be convergent. Conversely, if the cross-section increases gradually from the inlet to exit, the duct is said to be divergent. Steam turbine classifications. There are different classification criteria for steam turbines. In terms of stage design: impulse, reaction, combined type, single stage or multi-stage type. On the basis of supply of steam and steam exhaust condition. Condensing, non-condensing, back pressure. Extraction type. The impulse turbine consists of a set of stationary blades, followed by a set of rotor blades, which rotate to produce the rotary power. The high-pressure steam flows through the nozzles. The pressure energy of the steam decreases, which is converted to kinetic energy that gives high velocity to the steam. This high-velocity steam strikes the moving blades, or rotor, and causes them to rotate. The fixed blades do not completely convert all the pressure energy of the steam to kinetic energy, hence there is some residual pressure energy associated with the steam on exit. Therefore, the efficiency of this turbine is very limited as compared to the other types. It works on the principle that, for every action there must be an equal and opposite reaction, as previously discussed. A reaction turbine is constructed of rows of fixed and rows of moving blades. The fixed blades act as nozzles. The moving blades move as a result of the impulse of steam received, caused by change in momentum, and also as a result of expansion and acceleration of the steam relative to them. A form of turbine in which high-velocity steam produces an aerodynamic force as an impulse force as they move the turbine blades in the direction needed to spin the turbine blades. In this type of turbine, there is a stator vane and a rotor blade arrangement whereby the base area is an impulse design, and the top is a reaction turbine. The single-stage turbine consists of a single rotor. Steam is fed through one or several convergent nozzles. In the nozzle, steam pressure drops, and the velocity increases. In the rotor, energy is transferred from steam to the rotor. In impulse turbines, there is no pressure drop through the rotor, whereas in the reaction turbine rotor, pressure drops. If high velocity of steam is allowed to flow through one row of moving blades, it produces a rotor speed of around 30,000 revolutions per minute, which is too high for practical purposes. The multi-stage turbine consists of a set number of blades on the rotor. Each set of blades is called a stage. Each stage is an elementary turbine and consists of fixed guide vanes, along with moving rotor blades. Steam, which is heated H2O in the form of a gas, expands on the guide vanes. Its kinetic energy flow is converted on the rotor blades to work by turning the turbine's rotor. Inside a condensing turbine, steam expands below atmospheric pressure. It then condenses out while heating the cooling water in the condenser. In a straight condensing turbine, the total steam that enters the turbine goes to the condenser, and no steam is taken out from any stage in between the turbine. These are turbines in which the exhaust is above atmospheric pressure. Note: outlet steam from the turbine is at very low pressure. Back pressure steam turbines are widely used in process applications. In an extraction type turbine, steam is released between stages of the turbine, depending upon the industrial process needs. Remaining steam is condensed and recycled to boiler. Steam turbines, turbo expander. A turbo expander is a turbine through which high pressure steam is expanded. In other words, its pressure is reduced. Energy is produced in the process. This energy, which will otherwise be lost, is captured and used to drive a compressor or generator. Steam expansion is associated with drop in temperature and pressure, which causes condensation in the turbine. It is detrimental to turbines. The expansion of the steam is allowed to such a limit where its superheat is maintained. Steam turbines, general phenomena. The critical speed of a turbine is the point at which the natural frequency of a rotor is equal to its speed. This is usually expressed as a range. Assembled rotor consists of the rotor shaft with discs, blades, shrouding strips, etc. Deflection occurs during rotation of any rotating shaft, regardless of whether an external load is present or not. This deflection during rotation causes vibration in the shaft. Any object that vibrates will create sound wave. This is a natural phenomena. Vibrations occur at low speed as well as at high speed. When the shaft vibrates, it tends to vibrate at a particular frequency, or a set of frequencies. The frequency, or frequencies at which the shaft tends to vibrate, is known as the natural frequency. When one object vibrating at the same natural frequency of a second object forces that second object into vibrational motion, it is called resonance. It is easy to get an object to vibrate at its resonant frequencies, hard to get it to vibrate at other frequencies. A complex excitation of vibrating object will fall on its resonant frequency and vibrate at that frequency, effectively filtering out other frequencies. In 1940, the Tacoma Narrows Bridge collapsed when a steady wind provided the energy for the bridge to begin oscillating in simple harmonic motion. The amplitude of the oscillation continued to increase, and the bridge began twisting as well, until eventually it collapsed. It is also for this reason that marching army companies break step when traveling over bridges. Some machines tend to vibrate at a single frequency and produce a pure sound wave. Some machines tend to vibrate at a set of multiple frequency and produce a complex sound wave that is noisy. If the amplitudes of the vibrations are large enough and if natural frequency is within the human frequency range, then the vibrating shaft will produce sound waves that are audible. Machines naturally produce sound frequencies with complex wave characteristics. Different machines will produce different sound wave characteristics. Critical speed is the resonance condition when the speed of rotation is equal to the natural frequency of vibration. At critical speed, the shafts vibrate violently. The shaft should not be run at the critical speed, as the excessive deflection may cause failure of the shaft. Running a turbine at critical speed will result in catastrophic failure. First and second critical speed, high-speed turbines run above critical speeds. This gives a smoother and vibration-free performance. A turbine may have more than one critical speed, which may depend upon the number of couplings. The shaft passes quickly through the critical speeds, and no damage is done. The shafts are made with minimum possible thickness for very low critical speeds. As the rotor assembly spins, the rotor shaft with discs, blades, shrouding strips etc. have more than one critical speed. In the second critical speed, the entire length of the beam vibrates and deflects on two opposite sides. This will be generally 4 times the first critical speed. The running speed of the shaft, T, is between half and 2/3 times of the second critical speed. The turbine is provided with the overspeed limiter to shut the turbine operation down before it reaches the second critical speed. Thrust is a sudden push in a particular direction. The steam pressure and velocity differences across rotor blades and pressure differentials across rotor discs and rotor seals causes a thrust on the shaft. Because of this thrust, the shaft tries to move in the axial direction of thrust. To prevent the movement of the shaft, a thrust bearing is installed along the shaft. The speed of the steam turbine is maintained by a governor valve. The governor valve regulates the steam flow to the turbine to maintain a preset speed, set point, or preset load on the turbine. When this governor valve fails, the turbine runs into overspeed because of uncontrolled supply of steam. Couplings of the shafts are designed for a particular range of speed, and on overspeed, the coupling fails and damages catastrophically. Water ingress into a steam turbine can occur from a number of sources and may have catastrophic consequences. The blades may fracture and thrown out of the casing. A damaged blade on the rotor will cause vibration in the shaft. The shaft vibrations significantly increase while crossing the critical speed. A large steam turbine rotor must run with low vibration levels during operation and when going through critical speeds. Instrumentation will shut down the turbine when measured tolerances, set points, are exceeded. Catastrophic failure causes: out of alignment rotors, uneven heating, cooling or quenching of a hot rotor during operation, or after shutdown may cause bending of the rotor. Steam turbine, key components. A steam turbine has several key components. The components are: steam inlet valve, shutoff valve, governor, turbine, steam outlet valve, safety valve, drain valve, steam traps, steam strainer, turning gear, overspeed trip mechanism, lubricating oil system, cooling system. This picture shows schematics of a steam turbine from an operator's point of view. Steam inlet valve is a gate valve whose service is rated for high pressure and high temperature. This valve is opened when turbine is due to rotate. Shutoff valve and governor valve, they are the integral part of the turbine supplied by the vendor. Shutoff valve and governor valves are lined up in series. Shutoff valve has a function either to supply the steam or stop the supply of the steam. Governor valve has the function to control the speed of the turbine or the load of the turbine. Turbines have stators and rotors arranged alternately in series. The stator works as the nozzle to supply steam to the rotor. The rotors get energy from the steam to rotate the turbine. Safety valves are installed on surface condensers. The excess pressure is released to safeguard the piping and other auxiliaries. Steam lines have traps to eliminate any condensation. Steam lines have traps to eliminate any condensation. They recover and remove it by routing into a condensate header. They are installed at several places in steam lines. When a rotor is not turning, it has a tendency to sag due to its own weight. The turning gear is utilized on turbines to reduce eccentricity or out of round warping of the rotor. A turning gear, which has a separate motor, turns the rotor slowly, 10 to 300 rpm, through a clutching mechanism. This rotation keeps the rotor in balance. Before and after starting up, it is crucial to keep the turning gear operating, instead of allowing the rotor to come to a complete stop. Typically, the turning gear must be on for a defined number of hours, as per manufacturer for large steam turbines, before startups and after shutdowns. If a turning gear is not utilized, the rotor will become eccentric, possibly causing vibration damage. The speed governor controls the steam pressure and flow into the turbine. It operates on the principle of sensing turbine generator speed deviation from its nominal value and adjusting it to maintain a speed set point. If a load on the turbine increases, then there will be an increase in turbine speed to compensate. In order to meet the extra load, more steam to the turbine is required. The governor will open and supply more steam to the turbine to maintain speed. Similarly, when there is a sudden load drop, there is a decrease in turbine speed, and the governor reduces the steam flow in order to achieve the set point. SG, speed governor measures speed, and adjusts steam valves accordingly. CV, control valves manipulated by the speed governor, in order to maintain normal operating conditions. 4. Intercept valves, fully opened in normal operating conditions, or closed in case of severe overspeed conditions. MSV, RSV, main stop valve, and reheater stop valve, which is used as a backup in case of emergencies. Speed governors react when there is a change in load, a change in steam characteristics. If the temperature of the superheated steam drops, the valve will open more so as to deliver same amount of energy. Similarly, if the pressure of the steam drops, then the valve will open more. If a decrease in system frequency occurs, due to a loss of generation or an increase in load, the turbine shaft speed of each connected synchronous generator will also decrease. This speed decrease is transmitted to a mechanical governor fly ball assembly, by means of a shaft-mounted PMG, permanent magnet generator, and a ball head motor. As the fly balls spin more slowly, they move in, causing the valve to move up, and allow more flow of steam to the turbine. Similarly, the speed decrease is transmitted to an electro-hydraulic governor frequency transducer, by a toothed wheel or the generator potential transformers. The frequency decrease sensed by a frequency transducer, will be amplified, and used to open the valve. Thus, the output power of the turbine will increase and help arrest the frequency drop. A turbine may exceed the safe speed for a number of reasons: damaged turbine casing, due to overspeed. An overspeed trip shuts off the steam flow to the turbine, which causes the turbine rotor to decelerate. The trip mechanisms on most turbines are required by safety regulations to be tested periodically. A periodical overspeed test is in the interest of ensuring safety. Turbines produce large amounts of thermal and mechanical energy. Overspeed on a steam turbine can cause catastrophic turbine failure. If the rotational speed of the turbine exceeds the safe operating limits of the unit, the main shaft and impeller wheels can be pulled apart by centrifugal force. In the worst case, the disintegrating parts can break through the turbine housing, flinging hot, fast-moving sharp pieces of metal in all directions. The results of such a failure are always very costly and can be fatal to personnel in the area. Mechanical trip mechanism. Normal position. A chamber within the turbine shaft contains an overspeed bolt. The turbine shaft has an overspeed bolt that remains inside the cavity, and comes out excessively during overspeeding. The shuttle valve is held in place by a trip latch, spring A. Right end piston of the valve closes the oil dump line, so pressure between the two pistons is held. Hydraulic oil pressure is maintained to the fail-closed steam valve. If hydraulic oil pressure is lost, then spring B forces the valve to close. A small amount of oil passes between the piston and the cylinder wall of the trip system to allow for lubrication. Electronic trip mechanism. At least two speed sensors, A and B, are mounted on a multi-tooth speed pickup wheel. If a trip signal either from A or B is detected, then the turbine trips. If there is loss of signal or power for A and B, then the turbine trips. Overspeed trip mechanism consists of vibration sensors, speed sensors, multi-tooth wheel, overspeed bolt. A relay tachometer detects the speed of the turbine through pickup sensors. If the shaft exceeds its normal rotational speed, then a solenoid valve opens, releasing pressure that keeps the steam valve open to the turbine. Surface condensers are a major component of a steam turbine. It converts spent steam back into feedwater and returns it to the boiler. Turbine efficiency is increased by allowing for a maximum possible temperature and pressure difference between the superheated inlet steam and the condenser. Normally a shell and tube heat exchanger is used. Cooling water is the condensing medium used for condensing the steam. It flows inside the tubes. The surface condenser is held under a vacuum using steam ejectors. It condenses steam back into reusable feedwater. The exhaust steam condenses on the outside of the condenser tubes. The condensate is collected in the hot well, at the bottom area of the condenser. A condensate pump takes its suction from the hot well, and delivers the condensate to the deaerator of boiler system. Whenever the turbine load increases, the steam consumption in the turbine increases. Vice versa is also true. Although the steam consumption fluctuates with the load, cooling water flow is constant. When steam supply increases, the condensate temperature increases. As long as the condensate has a subcooled temperature, there is no effect on the exhaust pressure. If the condensate is not subcooled, then there can be a change in exhaust pressure depending on the extent of condensation. Condensation temperature is a function of steam pressure. As the vacuum increases, the condensation temperature decreases. To condense the maximum steam with the available cooling water temperature, surface condenser is operated under vacuum. Ejectors are used to create vacuum. It has no moving parts. In a steam turbine, ejectors are installed on the surface condenser to create vacuum. Ejectors are composed of three basic parts: a nozzle, a mixing chamber, a diffuser. An ejector has two inlets: one to admit motive steam, one to admit vapor that is to be evacuated. Motive steam enters at high pressure, low velocity. When expanded through nozzle, pressure energy is converted to velocity energy. A vacuum is created around in the chamber. Evacuating vapors are drawn in the chamber to fill the vacuum. Motive steam and evacuating vapors are mixed in the chamber and passes through the diffuser where some of the pressure energy is regained. Ejectors can be arranged as multi-stage systems with interstage condensers. The multi-stage arrangements allows lower suction pressures to be achieved than could be produced by a single-stage ejector. Interstage condensers economize on the use of motive steam, since the operating steam from stages upstream of the condenser is condensed, leaving only saturated incondensable gases to be handled by the succeeding stage or stages. Emergency shut-off valves are rapid and reliable interruption of steam supply to the turbine in case of activation of protection. Emergency shut-off valve, ESV, provides effective steam flow cut-off during emergency shutdown of the turbine manually or automatically. It adds a measure of safety critical to the turbine. It allows admission of steam for warm-up of the control valve during cold start. To start and stop the turbine and control its speed, the ESV is installed in the steam line just outside the HP valve chest. ESV is either fully open or fully closed. The ESV open fully when the turbine is reset, and remain fully open until the turbine is shut down, or an emergency such as overspeed trips the valves closed. The ESV mechanism is activated by means of an oil cylinder or solenoid. A manual latch lever is provided, which automatically disengages from the latch hook when tripped. A powerful compression spring is provided in the yoke, which forces the entire spindle mechanism against the seat. A hydraulic fluid pressure control oil is used to hold the valve open, and when the pressure is released the valve gets closed under steam pressure. Bearings support and are properly position the turbine rotor with respect to the stationary turbine parts. There are generally two types of bearings: journal or radial bearings. Thrust bearings. The journal, or radial bearings, support the weight of the rotor and position it radially. The thrust bearing absorbs axial forces on the rotor and positions it axially with respect to the stationary turbine parts. Journal bearing, tilting pad journal bearing. Turbines use journal bearings instead of ball or roller bearings. Journal bearings have a smooth surface of a soft material called babbitt. The bearings are fed with oil. As the rotor turns, it produces a pumping action that builds up pressure and a film of oil between the journal surface and the babbitt so that in normal operation the surfaces never touch. Thrust bearing. The thrust bearing builds up a thin film of oil between the bearing and a thrust runner on the rotor. Thus, the rotor never touches the bearing surface in normal operation. There may be many journal bearings for each turbine, however, there is only one thrust bearing. It is usually mounted on the non-drive end side. Steam turbines require a method of preventing steam from escaping from the casing at the region of the rotating shaft. The most common methods employed are labyrinths, carbon bushings. They do not seal perfectly but reduce the leakage. Seals are used to control the leakage of steam. The leakage may be between turbine stages inside the turbine, or where the shaft penetrates the turbine shells or casings. Seals, which are used to seal the penetration of the rotor through the turbine casings, or one turbine section from another, as in an HP/IP opposed flow section, are mounted in packing heads, or packing casings. The seals which seal the rotor at the penetration through the shells and casings are connected to the steam seal system. There are a number of different seal types, including carbon seals and labyrinth seals. Lubrication's oil system. The gears and bearings are the rubbing parts of the steam turbine and needs lubrication. Oil pumps supply the oil from reservoir to the bearings for temperature control and lubrication. Normally 2 pumps are provided. Main pump, driven off the turbine shaft or gearing shaft. Auxiliary pump, a gear pump, installed outside at the oil reservoir. The oil pressure is adjusted by setting the leak back through the lube oil relief valve. The oil pump discharge is routed through a filter followed by oil cooler. Oil filter and cooler both have standby arrangements. Cooling water flow is adjusted as per oil temperature requirement. The oil returned from the bearings is collected in a reservoir, where residence is allowed for separating solids and other contaminants. Thrust bearings, the axial thrust originates from. Steam thrust generated by the rotor parts are subject to steam pressure. The thrust forces developed in gear tooth. Thrust bearing has 2 functions. To constitute the axial reference point for locating the rotor in the casing. To carry the axial thrust. The thrust bearing consists of the bearing collar, integral part of the shaft. 2 rings of thrust bearing pads, each of which is provided with a tilting edge. By tilting the pads, a wedge-shaped gap can form between the bearing collar and the bearing pads. The space between bearing collar and pads is filled with oil. Because of its viscosity, the oil is forced from the surface of the rotating collar into the wedge gap. Because oil is practically incompressible, the decreasing flow section in the wedge gap must effect an increase of the oil pressure in the wedge gap. This oil pressure is balanced by the axial force of the rotor via the bearing collar. All steam supply lines are provided with condensate removal components, including correctly sized steam line, drip pockets, and steam trap stations. Steam traps collect all the condensate from the steam and route it to condensate header. Moisture in the turbine steam reduces turbine efficiency, erodes and corrodes turbine components, and increases the overspeed potential. Turbine efficiency is reduced by moisture in the steam, due to its retarding effect on the moving blades, and the disturbance of the steam flow by water droplets. 3 types of erosion, impact, washing, and wire drawing, can damage various turbine components. Water in steam supports various corrosion mechanisms, because it acts as an electrolyte, deposits impurities on the surface of heavily stressed components, and erodes away the protective layer. Wet steam increases the turbine overspeed potential, as water flashes to steam, upon a rapid pressure drop inside the turbine caused by cuffing off the steam supply. Float and thermostatic steam trap, thermodynamic trap. Steam traps are installed on the expansion loop lowest points, and before main steam valve. By removing the condensate from the steam lines, turbine's life is extended. Energy of superheated steam is conserved. Line is prevented from mechanical shocks, due to water hammering. Steam turbines, general startup steps. This is a general guideline for smooth startup of steam turbine. You must refer to the on-site approved procedure for starting the steam turbine. Note: this is an example only. Follow your approved documentation. Start the buffer gas. Start auxiliary lube oil pump, and circulate oil through all bearings and oil chambers. Blow the superheated steam outside. To remove condensates, establish cooling water circulation through tubes of surface condenser. Start circulation of condensate using condenser circulating water pumps. Start rolling the turbine with turning gear. Apply vacuum in the surface condenser. Start gland ejector steam, and apply sealing steam. Start the slow warm-up of the turbine. Put the control oil system on. Engage the latch of lever of main steam valve, or ESV. When the turbine casing temperature indicates a superheat, start the rolling of the turbine with superheated steam, and slowly stop the blow-off of the steam. The turning gear will automatically be detached once the turbine gets momentum from steam, better to observe physically. Roll the turbine at the idle speed, for even heating of all the parts of the turbine. Slowly raise the speed in given steps. Cross the critical speed, within the prescribed time, do not delay, otherwise enormous amount of vibration will take place. Once the minimum governor speed is reached, the governor valve takes the control of turbine speed. Once the governor valve takes the control of the speed, fully open the ESV valve. No speed. If during startup, then turbine was not rolled with turning gear. The initial torque required to rotate the turbine is high, and steam cannot supply that. If the turbine was running, and then observed that it has no speed, turbine tripped, and no one noticed, the reason of trip must be checked immediately, and recommended action must be taken. If allowed, then only roll the turbine with turning gear. Low speed. Main steam valve, ESV, governor valve is not sufficiently open. If main steam valve, or governor valve is not sufficiently open, it will not allow required amount of steam to enter. Steam pressure and temperature are not sufficient. The steam doesn't carry enough pressure and temperature energy to turn the turbines. Governor valve controller is not functioning. If controller has failed, then the valve will become stuck in one position, and steam entry will be restricted. Fluctuating speed. Fluctuating speed. Load on the turbine is fluctuating. When the load on the turbine fluctuates suddenly, the speed of the turbine fluctuates. Steam condition is not stable. When steam pressure and temperature energy are not stable, the turbine speed will fluctuate. Bearings, high temperature. Lube oil temperature is high. A high lube oil temperature results in high bearing temperature. In general, lube oil temp is kept 21 to 23 degrees Celsius, lower than the permissible bearing temperature. High lube oil temperature could be due to insufficient oil cooling or chocked oil filter, or oil deterioration. Imbalance of rotor shaft. If imbalance develops in the rotor shaft, one side bearing temperature will go high, where the another side bearing temperature will go low. Bearing is damaged. A high bearing temperature is the first sign of damage of bearings. This may result in change in characteristic sound of the turbine. High vibration. Damage to bearings. When the bearings are damaged, the turbine will develop high vibrations. Surging in connected compressor or blower. Because of the surging in the connected compressor and blower, the thrust continuously changes and develops high vibration. Imbalance of rotor shaft. If an imbalance of the rotor develops, the vibration levels change. This may be due to deposits or corrosion on the blades. Moisture in steam. Moisture in the steam gives additional impact on the turbine blades, which are uneven, so the turbine develops high vibration. High lube oil temperature. Insufficient cooling water flow through exchanger. Fouling in the exchanger will cause erratic temperature changes. Contamination in the oil, which causes fouling in the exchanger. When the exchanger oil is contaminated, its composition changes, affecting its ability to cool. Fouling of the exchanger affects the cooling ability of the lube oil. Bearing temperature is too high. If the bearing temperature is too high, the lube oil supply temperature will also increase. This will happen even if the cooling water flow is constant. Low lube oil pressure. Lube oil leaking through relief valves. Lube oil pressure is maintained by the use of pressure relief valves, PSV, in the system. Check PSVs to ensure they aren't leaking. Lube oil filter is blocked. Differential pressure between the high and low side of filters will increase as they become blocked. Change the filters. Changes in physical property of lube oil. There are different conditions that can adversely change the viscosity of lube oil. Testing will ensure that the oil maintains its lubricating abilities. If changes are detected, then either a full or partial oil change is needed.